Okay, this is take 3 of vector component addition. I've had people come in the room, disrupt while I've tried to record. Didn't matter because the next time I recorded the entire video, forgot to turn the sound on. So this is number 3, third time's a charm. Vector component addition. Essentially, vector component addition is to take those vectors that we've been working with, which are in polar coordinates, and convert them to rectangular coordinates. Add them up, and then we're going to change them back from rectangular to polar. The reason that you've got another method is because, as you probably noticed from the first standard, the more vectors added in, the more triangles you have to solve. So this is not really easier if you've only got a couple of vectors given. Law of cosines, law of sines isn't bad. Once we added in the third vector, well, you had to solve 2 triangles. So you can imagine as vectors are added on, it's going to create a whole lot more work to use trig. This method, while it's tedious and it's easy to make little mistakes, it is definitely easier to find the resultant vector. So let's just go about finding out how these formulas come to play. Here is a polar coordinate. We'll say it's got a magnitude of 21, miles, feet, inches, miles per hour, knots, whatever. It's got a direction of east 41 degrees north. That's a polar coordinate. We're going to convert that to a rectangular coordinate. So let's see, how does this come about? Well, a polar coordinate, if I graphed it on a rectangular coordinate plane, would look something like this. This being east, this being north. Those are the 2 directions here. So it's got a magnitude of 21 somethings and an east 41 degree north direction. So east, and then I'm going north 41 degrees. So approximately there. We'll say that's 21, and we ended right there. This angle, 41 degrees. We're going to find the x and y coordinate of that endpoint of that vector. So I'm going to drop this perpendicular to the x-axis and form a right triangle. The x-coordinate is how far over that coordinate is, and the y-coordinate is how far up that is. If we go back to right triangle trig, this is the adjacent side to this angle. This is the opposite side to this angle. So if I wanted to set up a way to find x and y coordinate, I'd use the cosine because it's adjacent and hypotenuse, and so the cosine of 41 degrees would be equal to x over 21. And then to solve that, x would be equal to 21 times the cosine of 41. And if I want to find the y coordinate, then I would say it's the sine of 41 because it's opposite and hypotenuse is equal to y over 21, which y would be equal to 21 times the sine of 41. So I take my calculator, type in those numbers, 21 times cosine of 41. My rectangular coordinate would be 15 point, and I want to take it at least 3 decimals, but in this case the 9 would round the 8 to to a 9. So this is going to be 8, 4, 9. And then I'm going to find the y-coordinate. So 21 times the sine of 41. And then I get 13.777. So your x and y coordinate here are pretty close to each other. That should make sense to you because the distance being 41 degrees is really close to the center point, which is 45 degrees. If you'll think back to the unit circle, that's where the x and the y were the same. Square root of 2 over 2, square root of 2 over 2. And so the x and the y here are going to be pretty close to each other because that's almost in the middle of that quadrant. Let's go back here and just look at what would be the general formula if we hadn't necessarily been given numbers. Well, the x-coordinate would have been whatever this magnitude was. In this case it was 21, but the magnitude of the vector times the cosine of the angle, theta. And the y-coordinate would be the magnitude times the sine of theta. That should make sense to you because in the first unit we learned that cosine is the x and sine is the y. So let's try another one. Let's say we've got a polar coordinate of 32 miles and a direction of west 13 degrees south. And we're going to change that to our rectangular. So let's see what that looks like on a coordinate plane. West and south. 13 degrees isn't much. Here's the west. I'm going to go south 13 degrees and there's my vector. 32 magnitude. This angle is 13 degrees west-south. So I'll take my perpendicular to the x-axis. I'm going to use these two general formulas right here, but with the information of 32 and 13. So the x-coordinate would be 32 times the cosine of 13, and the y-coordinate would be 32 times the sine of 13. So let's see what those come out to be. 32 times the cosine of 13 is 31.17. Well, now this one I'm going to have to take the 8 to the 9, but then the 9 would go up, so actually 31.18. And the y-coordinate would be 32 times the sine of 13, which is 7.198. There is a reason I left some space in there, is because if you'll go back and think about this particular coordinate is in quadrant 3. And in quadrant 3, I know that both the x and the y are negative. So it also means that my x and my y coordinate has to be negative. So there's one of the things you have to remember, depending on the direction, what the signs of your coordinates need to be. So you can either make yourself remember, or we can do it another way, where your calculator remembers for you. If we wanted to change this to an angle between 0 and 360, this would be 0, 90, 180, and so the angle actually for this would be 180, and then we'd have to add on 13 more degrees, so the angle instead of west 13 south could also be considered a 193 degree angle. So I could go back to my formula here, and I could actually use x equals 32 times the cosine of 193, and y would be equal to 32 times the sine of 193. Let's see what the calculator gives us for those. 32 times the cosine of 193 gives us the negative 31.18. And if we do 32 times the sine of 193, the calculator gives us our negative 7.198. So either convert between 0 and 360 to give you the correct sign, or just remember by direction that west and south are both negative directions. West is negative on the x and y coordinate, south is negative on the x and y coordinate. One other thing, we could just look at these numbers, 31 and 7. Over 4 times as big. If you look at a 13-degree angle, it makes sense that it went over a lot more than it went down. So my x-coordinate should be quite a bit larger than my y-coordinate. The next video will teach you a little bit more how to use these components in order to actually figure out component addition for solving for resultants.